Okay, let's continue with section 14.2 and discuss the autoionization of water. Like I told you before, I told you water is amphiprotic. Amphiprotic and amphoteric are the same thing. It can act as as an acid or a base, which means it can donate and accept a proton or hydrogen ion. So this is your formula for the autoionization of water. Here, water is acting as an acid. It's donating a proton to water as a base. And what happens is what's left over from this water after it loses a hydrogen is the hydroxide ion. After this water accepts the hydrogen ion, it's left with the hydronium ion. So then we have two water molecules that are liquids in equilibrium with a hydroxide ion and a hydronium ion. Okay? So think about if we were going to write the K expression for this reaction. The K would equal the concentration of the hydroxide ion times the concentration of the hydronium ion, and we do not put it over the concentration of water squared because water is a liquid that you see here. So this does not affect the equilibrium, and it does not go into our equilibrium expression. This K happens to be called Kw for water, which we'll talk about on the next slide. So the equilibrium expression for water is Kw. Kw equals hydronium times hydroxide, just like we did before. There's no water because water is a liquid and it doesn't go in our equilibrium expression. That's from chapter 13, if you remember that. From experiment, it is known that at 25 degrees Celsius, pure water has an equal concentration of hydronium and hydroxide ions. You may have heard this before where we said a solution of water is neutral. That means the acidic ions are in the same concentration of the hydroxide ions. So in pure water, hydronium and hydroxide are equal, and that number happens to be 1.0 times 10 to the minus 7, and there should be a unit behind that says molarity. Okay? So that is the concentration of those in pure water at 25 degrees Celsius. So if both of those values are 1.0 times 10 to the minus 7, then we can just square 1.0 times 10 to the minus 7, and we get this number, 1.0 times 10 to the minus 14. So Kw, this is put a big star beside this because you need to memorize. Kw is 1.0 times 10 to the minus 14 at 25 degrees Celsius. Okay? If the temperature changes, K can change. So in a neutral solution, the hydronium and hydroxides are the same. Acidic solutions have more hydronium. Basic solutions have more hydroxide. These numbers can change, but when you multiply them together at 25 degrees Celsius, they have to equal Kw because it's a constant. Okay, now let's calculate the hydrogen ion and hydroxide ion for these solutions that are at 25 degrees Celsius. I'm going to do A, and I'll let you do B and C on your own, but I will give you the answers for B and C. Okay, so for part A, if we know that Kw is equal to the concentration of hydrogen ion times hydroxide ion, which equals 1 times 10 to the minus 14, we can substitute and solve for our unknown. So if hydroxide is 1 times 10 to the minus 5, and hydrogen is what we're solving for, and that all equals 1 times 10 to the minus 4. You can divide both sides by 1 times 10 to the minus 5 and solve for the concentration of H+. And you should get that is 1.0 times 10 to the minus 9. And that unit is molarity, so that's your answer for part A. You do B and C the same way. Solve for whatever is unknown. So for B, you should get 1.0 times 10 to the minus 7. And for C, you should get 1.0 times 10 to the minus 15. Okay? So try B and C on your own and make sure you get these answers. Okay, for this exercise, it's giving us that at 60 degrees Celsius, the value of kW is 1 times 10 to the minus 13. And we know that at 25 degrees Celsius, kW is 1 times 10 to the minus 14. Using Le Chatelier's principle, we're going to predict whether the autoionization of water is endothermic or exothermic. And then we're going to calculate hydrogen and hydroxide ions in a neutral solution at 60 degrees Celsius. So the first thing I'm going to write down is that at 25 degrees Celsius, we have our kW as 1 times 10 to the minus 14. At 60 degrees Celsius, it's 1 times 10 to the minus 13. You should be able to see as the temperature increased, kW also increased. And we know that if kW increased, then the concentration of products had to increase, okay? So that was an increase in the concentration of products, which are hydronium and hydroxide in this case. Okay, so there's an increase in concentration of the products. I have two options for my reaction. Either I can have heat on the reactant side to yield products, or I can have heat on the product side. In the first case, this one is endo and exo. So we're going to look at it and see which one happened. All right. Since we increase temperature, I'm going to see what happens if I increase the temperature of each of these reactions. In the first case, if I increase the temperature, temperature's increased on this side, which shifts the reaction to the right to make more products. In the second case, if I increase the temperature, I increase the heat on the product side, and the reaction shifts to the reactant side. In our case up here, we made more products. So there was a product shift. So that tells me that this reaction shifted to the right to make more products, and it is endothermic. So this particular reaction for the autoionization of water is endothermic. In part 2, we have to calculate hydronium and hydroxide ion concentration. For a neutral solution, those should be the same. So I can just set 1 times 10 to the minus 13 equal to, I'm going to call it x squared. Take the square root of both sides, and you should get 3.2 times 10 to the minus 7. Using significant figures, that's just 3 times 10 to the minus 7. And that is the concentration of hydronium and hydroxide in a neutral solution at 60 degrees Celsius. Okay, and the pH scale is a logarithmic scale with a base of 10. A P in math is a function, it's a mathematical function that says to take the negative log of something. So the P in pH means negative log. The H in pH stands for hydrogen ions, okay? Because pH tells you how acidic something is, and acidity is based on the number of hydrogen ions in the solution. So if there's 1 hydrogen ion out of 10 ions in solution, the pH is 1. If there's 1 out of 100, then the pH is 2. You can count those zeros. If there's 1 out of 1,000,000, then here the pH would be 6. So you can see as pH decreases, a solution becomes more acidic. This solution with pH 1 has a lower ratio than the solution of 1 out of 1,000,000, so it's a more acidic solution. Okay? I do want to mention here, put a big star beside this. pH does not determine acid strength. It determines how concentrated an acid is. So if I have an acid that has a pH of 2, that tells me that it's a very concentrated acid. It doesn't tell me it's strong. Okay? I can have a weak acid like acetic acid that has a pH of 2, but it's still a weak acid. It's just highly concentrated. If I have a solution that's pH of 6, that's still an acid. It's less concentrated, but it can be a strong acid like sulfuric acid. So The pH does not determine how strong an acid is. It determines acid concentration. This slide is just showing you the pH scale from 0 to 14. Anything above 7 is basic, below 7 is acidic, and anything that's at 7 is neutral. This is just a basic scale. Experiments have been done to show that it is possible to have negative pHs and pHs above 14. Okay, so let's look at how to calculate pH. Our regular formula for P, since P is a P function, it means to take the negative log of something. So pH is the negative log of hydrogen ion concentration. Then I can also calculate pOH. I take the negative log of hydroxide ion concentration. When you add these two together, you should get 14, which is also the pKw. What is pKw? It's the negative log of the Kw. And we know Kw is 1 times 10 to the minus 14. So if you take a moment to do the negative log of 1 times 10 to the minus 14 in your calculator, you should get 14.00. If I want to do the reverse process of pH in calculating the hydrogen ion concentration, I do 10 to the negative pH as my exponent. So it's called the anti-log of the negative pH. And the same for hydroxide. When you multiply these two numbers together, you should get 1 times 10 to the minus 14 as long as it's at 25 degrees Celsius. That's our Kw. With significant figures, you look at the number of significant figures in your hydrogen ion concentration, and that should match the number of decimal places in your pH. So for this example, there are 2 significant figures here in my hydrogen ion concentration. So the pH should go 2 places past the decimal. And if you do that in your calculator, you should get 9.00. In this exercise, we're calculating the pH and pOH for 2 different solutions. In the first solution, they give you the concentration of hydroxide ion, and the second, they give you the concentration of hydrogen ion. I'm going to start with the first one. Since they give me the concentration of hydroxide ion, I can start with finding the pOH because that'll be the easiest for me to find first. So for part A, the pOH is equal to the negative log of 1.0 times 10 to the minus 3. You do that in your calculator and you should get that the answer is 3. So the pOH is, since there's 2 significant figures here in my concentration, I need 2 decimal places in my pOH. So it would be 3.00. pH plus pOH should equal 14. Okay? So that tells me that the pH is 11. Okay, let's try part B. Since I'm given the hydrogen ion concentration, this time I'm going to find pH. And that's the negative log of 1.0. If you do that in your calculator, you should get that the pH is 0. And the pOH then is 14.00. Okay, so in this one, the pH of blood is 7.41. Calculate pOH, H plus, and OH minus concentrations. The pOH, if I do 14 minus 7.41, I should get 6.59. And then to calculate the hydrogen ion concentration, that's going to be the anti-log of the negative pH. And if you do that in your calculator, you should get 3.9 times 10 to the minus 8, and the unit is molarity. 2 significant figures since there's 2 places behind your pH. And you do the same thing for OH minus. It's going to be 10 to the negative 6.59. Do that in your calculator and you should get 2.6 times 10 to the minus 7. 2 significant figures because 2 places past the decimal. There's more than one way to do this, but you need to be able to do these calculations pretty quickly. pH and pOH calculations are just a small part of a larger process that we're going to do later on, so it's important that you're able to do these calculations very quickly.